Hello and welcome to A-Level Geography Explained. In this video, we will be exploring the first inquiry question of the coasts topic. The three main subsections of the inquiry question covered are the features and landscapes of the coast and wider littoral zone, the influence of geological structure, and the influence of lithology. Let's begin. The littoral zone is the wider coastal zone including adjacent land areas and shallow parts of the sea. It is the boundary between land and sea. To help explain this term in detail, let's look at a diagram and explain each section of the zone. The littoral zone is divided into four main sections: backshore, foreshore, nearshore, and offshore. The backshore lies above the high tide mark and is only affected by the sea during storms or very high tides. Features here include storm beaches, formed by strong waves throwing pebbles inland, and berms or shingle ridges, built up by gentler wave action. The foreshore, or intertidal zone, lies between high and low tide marks. It's where most wave and tidal action takes place, leading to constant erosion, deposition, and transport of material. You'll often find sand runnels here, small channels formed as water drains back to sea. Beyond this is the nearshore, which stretches from the low tide mark to where waves begin to break. This high-energy zone is where underwater features like longshore bars form as waves stir up and move sediment. Finally, the offshore zone lies beyond the breaker zone, where wave energy weakens and sediment movement is minimal. It's more stable but still supplies material to the coast over time. Tides are key in this zone. Low tide exposes the foreshore, high tide covers it, and spring tides, the highest, can reach into the backshore, especially during storms, influencing how and where coastal processes occur. The littoral zone is constantly changing due to long and short-term factors. In the long term, climate change and the resulting changes in sea level influence the littoral zone. In the short term, the variations between high and low tides and the energy differences between individual waves can impact the environment. Types of coast. There are two types of coast: rocky coastlines and coastal plains. Let's take a look at the features of each. Firstly, rocky coastlines. These are also known as cliffed coastlines and are areas of high relief. They have resistant geology, meaning they erode more slowly, and are found in high-energy environments with destructive, powerful waves. Coastal plains are also known as sandy or estuarine coastlines. They have a low relief with beaches or shallow sand dunes. They have less resistant geology compared to rocky coastlines and are a low-energy environment. This next section of the video will cover concordant and discordant coastlines. Concordant coastlines are where the rock strata runs parallel to the sea. This means that only one type of rock is exposed at a time. Let's take a look at some real-world examples of this. Half coastlines are where long sediment ridges topped by sand dunes run parallel to the coast just offshore, creating lagoons, halves, between the ridges and the shore. Secondly, a Dalmatian coastline forms when valleys, formed by folding, running parallel to the coast are flooded by rising sea levels, resulting in long, narrow islands and narrow channels called sounds. A final example, that is one of the most famous coastal locations in the UK, is Lulworth Cove. The cove formed as a result of differential erosion where softer rocks like clay and sands were eroded more quickly than the harder limestone at the front. Waves broke through a gap in the limestone and eroded the softer rock. Discordant coastlines are where different types of rock run perpendicular to the shore. This means layers of hard and soft rock alternate along the coast. You can see in this diagram how different rates of erosion can occur. On discordant coastlines, headlands and bays form. Over time, the softer rock, like clay or sand, erodes more quickly than the harder rock, like limestone or chalk. This uneven erosion creates bays where the soft rock has worn away, and headlands where the hard rock is left protruding. In the diagram, we can see how wave energy behaves around these features. Wave energy converges on the headlands, meaning it's more concentrated and powerful there. This leads to intense erosion, which can form features like cliffs, caves, and arches. Meanwhile, wave energy diverges in the bays, making the energy weaker. This creates calmer conditions, where sediment is deposited, forming quiet beaches. Over time, sediment is moved from the headlands into the bays, further shaping the coastline. So in short, headlands are eroded, bays are sheltered, and the coastline becomes more irregular due to differential erosion. Geological structure is key to understanding coastal landscapes. The geological structure is the way that rocks are folded or tilted. This is known as its lithology. There are some key definitions to learn. Strata is the layers of rock. Bedding planes are horizontal cracks created by separations in the formation of sedimentary rocks. Joints are vertical cracks caused by tectonic activity. Folds are the result of pressure during tectonic activity causing the rock strata to fold. Faults are the result of stress causing the rock to fracture. And the dip is the angle of the rock strata. These features can be exploited by erosional processes to create microfeatures such as caves and wave-cut notches, as shown in these photos. There are three main rock types to know, so you can identify potential causes of differential erosion on coastlines. Igneous rocks are formed from solidified lava. Metamorphic rocks are formed by the recrystallization of sedimentary and igneous rocks through heat and pressure. And finally, sedimentary rocks are formed as deposited sediments are compacted. There are four cliff profiles to know. They are horizontal dip, seaward dip, low angle, seaward dip, high angle, and landward dip. Firstly, horizontal dip. This cliff profile is vertical or near vertical in profile. Notches in the cliff reflect the strata that is more easily eroded, and there can be some small-scale mass movements in this cliff profile. Seaward dips may exceed 90 degrees. This results in areas of overhanging rock forming. Consequently, this can make the profile very vulnerable to rock falls. A low-angle seaward dip has a profile that slopes towards the sea. One rock layer faces the sea and it is very vulnerable to rock slides. Landward dips feature steep profiles and very few rockfalls. This creates a very stable cliff. The final part of this video will look at vegetation and succession. Firstly, here are two definitions to include in answers on this topic. Halophytes are plants that can tolerate salt water such as reeds. Xerophytes are plants found in arid or dry climates that can withstand harsh environments. Let's discuss sand dune succession. Sand dune succession, also called a samosia, is the natural process by which plant communities develop over time on coastal sand dunes, moving from bare sand to mature woodland. It's a great example of plant succession in action. It starts at the beach, where wind deposits dry sand just above the high tide line. This creates small embryo dunes, colonized by pioneer plants like sea couch grass and sea rocket. These plants are adapted to survive harsh, salty, and dry conditions. They trap more sand and begin to stabilize it. As more sand accumulates, larger fore dunes and yellow dunes form, dominated by marram grass, which has deep roots and can tolerate burial by sand. These dunes are still quite mobile and have a yellow color due to the high sand content. Further inland, the dunes become more stable and less salty, forming gray dunes, named for their darker soil and the presence of plants like gorse. Organic matter from plants begins to build up in the soil, improving fertility. Between dune ridges, low-lying areas called dune slacks form, where water collects and the soil is more moist. Here, you'll find grass, heather, and sedge growing. Eventually, if conditions allow, pine woodland or other types of climax vegetation develop, marking the final stage of succession. These areas are sheltered from wind and salt spray and support more complex ecosystems. Salt marsh succession, a type of halosia, is the process by which vegetation gradually colonizes and develops on low-lying coastal mudflats in sheltered estuaries or behind spits, where wave energy is low and deposition can occur. It starts with mudflats, where fine sediment is deposited by tides and rivers. At first, the area is bare and frequently flooded by salty seawater. As more mud builds up, pioneer species like eelgrass and glasswort begin to grow. These are halophytes. As the pioneers trap more sediment, the land level rises and flooding becomes less frequent. This allows other plants like sea lavender and cordgrass to grow. These species help stabilize the marsh further and improve the soil by adding organic matter. Over time, more complex vegetation such as meadow grasses, rushes, and even shrubs colonize the higher areas of the marsh, where conditions are less salty and better drained. These areas are only occasionally flooded. Eventually, if the land continues to build and flooding becomes rare, the marsh may develop into coastal woodland or be reclaimed for agriculture. This final stage is known as the climax community. Second inquiry question of the coasts topic. The three main subsections of the inquiry question covered are marine erosion, coastal landscapes, sediment transport and deposition landscapes, and subaerial processes. Let's begin. Firstly, here are some key definitions to help understand waves. Fetch is the uninterrupted distance across water over which a wind blows, and therefore the distance waves have to grow in size. The swash is the flow of water up a beach as a wave breaks. And the backwash is the movement of water back down the beach. Constructive waves have a strong swash and a weak backwash. This means they build up the beach. The waves have a wave height of less than 1 meter and a long wave length. They also have a low frequency and are formed in calm conditions. Destructive waves have a weak swash and a strong backwash. This means they take sediment away from the beach. The waves have a wave height of more than 1 meter and a shorter wavelength. They have a higher frequency and are formed in higher energy environments. Now we will look at erosional processes. There are 4 main types of erosion to know. Hydraulic action is when air trapped in cracks and fissures is compressed by the force of waves crashing against the cliff face. Abrasion is where sediment picked up by breaking waves is thrown against the cliffs. Attrition is when sediment hits each other, becoming smaller and rounder. And finally, corrosion is where carbonated rocks are vulnerable to solution by rainwater and sea spray. For each type of erosion, geological features can influence vulnerability. Rocks with fissures are more vulnerable to hydraulic action. Attrition is more impactful on softer, less resistant, sedimentary rocks. Attrition has a larger impact on softer rocks because they reduce more rapidly in size as they hit other rocks. Corrosion has a bigger impact on limestone as it is vulnerable to weak acids found in rain and seawater. Erosional processes create distinctive landforms. This diagram shows the erosion of a headland. The process begins with a cliff, which is a steep rock face along the coastline. Waves constantly hit the base of the cliff, especially where there are natural weaknesses such as cracks or faults. Over time, the force of hydraulic action and abrasion enlarges these cracks. Eventually, a cave forms in the side of the cliff as the rock is worn away. As erosion continues, the cave deepens and may eventually break through to the other side of the headland, forming a natural arch. This arch is an impressive structure with a bridge of rock over the water, as seen in the middle of the drawing. The arch remains temporarily stable, but the same forces that created it continue to act on it. With time, the roof of the arch becomes too weak to support itself and collapses due to gravity and further erosion. This leaves behind a tall, isolated column of rock called a stack. The stack stands alone in the sea, separate from the rest of the coastline. Eventually, the stack is also worn down by wave action and weathering. As it gets smaller and shorter, it becomes a stump, a small, flat piece of rock barely rising above the sea level. This marks the final stage of this coastal landform sequence. Wave-cut platforms are exposed at low tides. They are left after cliffs have retreated. Wave-cut notches are the early stages of this process of recession. At the base of cliffs, erosion is more rapid, as hydraulic action and other erosional processes are more intense. Now we will look at the 4 types of transportation. Traction is when sediment rolls. Saltation is where lighter sediment is bounced. Suspension is where very light material is carried in a body of water. And solution is when dissolved sediment is carried in water. Here is a diagram illustrating the transportation process of longshore drift. It occurs when waves approach the shore at an angle, usually due to the direction of the prevailing wind. When a wave breaks, the swash carries material up the beach at the same angle as the wave. The backwash then pulls the material back down the beach at a right angle, due to gravity. This creates a zigzag movement of sediment along the coast, gradually shifting material such as sand and shingle in the direction of the prevailing wind. Here are two types of deposition. Gravity settling occurs when the energy of water becomes too low, and sediment is deposited starting with the heaviest. Flocculation is where small particles clump together due to chemical attraction. Now we will look at some landforms created by transport and deposition. A recurved spit is a narrow strip of sand or shingle that extends out from the coast into the sea and curves inward at the end. It begins to form through the process of longshore drift, which transports sediment along the coastline in the direction of the prevailing wind. When the coastline suddenly changes direction, such as at a river mouth or bay, the sediment continues to be deposited out to sea, gradually building up a long, narrow ridge known as a spit. As the spit extends further, it becomes more exposed to waves from different directions. The tip of the spit is then curved inland by wave refraction and changing wind directions. This curved end is what gives a recurved spit its distinctive hook-like shape. Behind the spit, sheltered water allows finer sediments to settle, sometimes leading to the formation of salt marshes or mudflats. An example of a recurved spit is Spurn Head, on the Holderness coast in England. An offshore bar is a ridge of sand or shingle that forms parallel to the coast, but offshore, beneath the surface of the water. It usually forms when waves break before reaching the shore, often due to a gentle beach gradient or a large supply of sediment. As the waves lose energy, they begin to deposit sediment in the sea, just off the coastline. Over time, this builds up into a submerged or partially exposed ridge. This is the offshore bar. Another way offshore bars can form is when strong backwash pulls sediment away from the beach, especially during storm conditions, depositing it in deeper water. This material can then accumulate and create a bar offshore. Offshore bars can reduce wave energy reaching the coast, acting as a kind of natural barrier, which helps to protect the beach from erosion. A coastal bar is a ridge of sand or shingle that forms across the mouth of a bay or river, connecting two headlands and blocking off the water behind it. This often creates a lagoon between the bar and the mainland. The process begins with longshore drift, which transports sediment along the coastline. When the coastline has a bay or indentation, wave energy decreases in that sheltered area, causing deposition of the sediment being carried. Over time, this deposition continues and extends across the bay, eventually joining the two sides. Once the bar has completely blocked the bay, a lagoon or coastal lake can form behind it. Coastal bars typically form on coasts with low wave energy and plentiful sediment supply. A tombolo is a sand or shingle bar that connects an island to the mainland or to another island, effectively linking two landmasses. The process begins when waves approach the island from different directions. In some cases, wave refraction can cause the waves to lose their energy in the areas around the island. This energy loss leads to deposition of sediment in the water between the island and the mainland. As sediment accumulates, it gradually builds up a narrow strip of land, called a tombolo, which eventually connects the island to the mainland. This happens when the longshore drift and wave action combine to deposit material in the sheltered area between the island and the mainland. A tombolo is often temporary, as erosion and further wave action can cause it to change shape or disappear over time. However, it remains a significant landform in areas with low wave energy and abundant sediment supply. Let's look at sediment cells. A sediment cell is the sourcing, transfer, and deposition of sediment along a stretch of coastline. There are 11 around England and Wales. Temporary sinks are dunes and beaches. Transfer methods include longshore drift and offshore currents. A more permanent sink is an estuary. Each sediment cell operates in a state of natural equilibrium, meaning that sediment inputs balance outputs to sinks. The amount of sediment available to the cell is the budget. Sediment cells can experience positive and negative feedback. An example of negative feedback is if a major cliff collapse occurs and rock debris protects the base of the cliff. Therefore, erosion is reduced. This allows the system to return to equilibrium. Positive feedback is caused by sea level rise, as this can create increased erosion of spits and estuaries, meaning sediment is removed faster than it is replaced and disequilibrium caused. Now we will look at subaerial processes. A key point to note is the difference between erosion and weathering. Erosion is the breakdown of rock due to the action of an external force. Weathering is the breakdown of rock in situ, by chemical, mechanical or biological agents. There is no movement. Here are the three weathering types. Firstly, mechanical. Two types of mechanical weathering are freeze-thaw weathering and salt crystallization. Freeze-thaw weathering happens because water expands by 9% when freezing, exerting a force on cracks and fissures. Any rocks with cracks and fissures are vulnerable to this. Salt crystallization is where the growth of salt crystals in cracks and fissures can break them apart. Porous rocks are vulnerable to this. Next is chemical weathering. Here are three types. Carbonation is the slow dissolution of limestone due to weak acids in rainfall. Hydrolysis is the breakdown of rocks and minerals by chemical reactions with water, resulting in the formation of new minerals and the release of ions into solution. Oxidation occurs when oxygen reacts with minerals in rocks, especially those containing iron, leading to the formation of oxides and a reddish-brown discoloration, weakening the rock structure. Finally, biological. Plant roots growing in cracks and fissures force rocks apart, and this is an important process on vegetated cliff tops. Rock boring is caused by many species of clams and mollusks digging into rock and may also secrete chemicals that dissolve rocks. Sedimentary rocks in intertidal zones are vulnerable to this. The last part of this video will look at mass movement. Mass movement is the downslope movement of material under the force of gravity. Rotational cliff slumping is an example of this. It occurs when a section of a cliff or coastal slope moves downward and rotates along a curved surface. It usually happens in areas with weak or unconsolidated materials like clay, soil, or sandstone. The process begins when water infiltrates the cliff, which increases the weight of the material and reduces its stability. Over time, waterlogged material becomes more prone to slumping. The material at the top of the cliff becomes saturated with water, and the weight causes the cliff to become unstable. The cliff face then slumps down along a curved slip plane, moving as a block of earth that tilts backward. This movement often results in curved scars on the cliff face and may create terraces of material. The rotational motion of the slump causes the material to move in a semicircular or arc-shaped path. This type of slumping is common on coasts with steep cliffs, soft rocks, and heavy rainfall. It can significantly change the coastline by causing erosion and loss of land. Hello and welcome to A-Level Geography Explained. In this video, we will be exploring the third inquiry question of the coasts topic. The three main subsections of the inquiry question covered are changes in sea level, rapid coastal retreat, and coastal flooding. Let's begin. Firstly, we will look at longer-term sea level rise. Here is the impact that the last ice age had on sea levels. During the last ice age, the sea level was much lower than it is today, at least 394 feet lower. This dramatic drop in sea level exposed large areas of land that are now submerged. The continents were more expansive, and the coastlines looked very different compared to what we see now. As the ice began to melt, the rising sea levels brought about significant changes to the landscape. The rise in water levels led to the formation of new landmasses and the flooding of previously dry areas. Notably, this process was responsible for the appearance of regions like Britain and the islands of Southeast Asia. Additionally, the rising waters filled the Hudson Bay, altering the geography of that region as well. Post-glacial adjustment is another cause of longer-term changes in sea level. During the last ice age, thick ice sheets pushed down the land in northern UK. When the ice melted, the land began to slowly rise again. This is called post-glacial adjustment or isostatic rebound. Scotland is rising, while southern England is sinking, as the land readjusts. This causes relative sea levels to fall in the north and rise in the south, increasing flood risk in places like London. Post-glacial adjustment is a type of isostatic change, and it's still happening today thousands of years after the ice melted. Now we will look at eustatic and isostatic changes in sea level. Here are the definitions of both. Isostatic change is a local rise or fall in land level. Eustatic change is a rise or fall in global water level, caused by a change in the volume of water. Marine regression is where sea level drops, exposing more land. This creates an emergent coastline. Eustatic fall can cause this. During glacial periods, water is locked up as ice and global sea levels fall. Isostatic falls creates this after ice sheets melt. This means the land rebounds slowly, and the land rises out of this sea. We will look at the landforms this creates later in the video. Marine transgression is where sea level rises, submerging more land. This creates a submergent coastline. Eustatic rise can cause this. After glacial periods, water locked up as ice melts and global sea levels rise. Also, thermal expansion can occur as a result of global warming. Isostatic rise can cause this by sediment accretion. This can create a slight crustal sag, especially at deltas. Here are the two main landforms created by emergent coastlines. The image below shows raised beaches and fossil cliffs. As land rises, it can cause old beaches and cliffs to be lifted above sea level. When the land rises, these former coastal features, such as beaches that were once shaped and constantly affected by waves, become elevated above the reach of the sea. These raised coastal features are referred to as raised beaches. They stand as evidence of past sea levels and offer a glimpse into how the coastline once appeared when the sea level was higher. Behind these raised beaches, you'll often find what are called fossil cliffs. These are cliffs that were once directly eroded by the action of the sea but have now been elevated inland due to the rising land. There are three main submergent coastline formations to know. Firstly, rias. A ria is a drowned river valley formed by eustatic sea level rise, flooding the lower course of a river. It has a V-shaped cross-section, is deepest at the mouth and shallower inland. An example of this is the Kingsbridge estuary in Devon. This is shown below. Next, fjords. They are very similar to rias, so it is important to know the difference. A fjord is a drowned glacial valley, formed when eustatic sea level rise floods a U-shaped valley carved by a glacier. Fjords are typically steep-sided, deep, and straight, with the deepest water inland and often have a shallow mouth. In comparison, rias are V-shaped and formed by rivers, fjords are U-shaped, steeper, deeper, and formed by glacier. Finally, Dalmatian coasts are formed when rising sea levels flood parallel mountain ridges and valleys. The land sinks, leaving behind a series of long, narrow islands running parallel to the coast. This coastal feature is common in areas with tectonic activity and folded mountain ranges. Now we will look at contemporary sea level change. Global warming can cause sea level change due to three main factors: thermal expansion, the melting of mountain glacier, and the melting of ice sheets. Thermal expansion occurs when ocean water warms up and expands, taking up more space. As the Earth's temperature rises, the oceans warm, causing the water to expand and contribute to rising sea levels. The melting of mountain glacier is another major factor. As global temperatures increase, glacier in mountain regions are melting, adding more water to the oceans. This includes glacier in areas like the Himalayas and the Andes. Lastly, the melting of ice sheets in places like Antarctica and Greenland is a significant cause. Ice sheets hold vast amounts of frozen water, and as they melt, they release large amounts of water into the oceans, further raising sea levels. Estimates of future sea level rise vary because scientists have to consider all these factors, and the exact outcome depends on future climate conditions and human actions. While some estimates predict a small rise, others suggest a larger increase. These estimates can change based on new data and better understanding of how climate systems work. In some locations, the rising of sea levels can be influenced by tectonic activity, particularly through earthquakes. Successive major earthquakes can lift or lower the land, causing sudden changes in the elevation of coastlines. This process is known as tectonic uplift. When an earthquake occurs along a fault line, the land on one side of the fault may be pushed upward or downward, altering the local sea level in that area. A notable example of this can be seen in the aftermath of the 2004 Indian Ocean earthquake, which caused the devastating Indian Ocean tsunami. The earthquake, which struck off the coast of Sumatra, lifted some nearby islands by up to 2 meters above sea level. This dramatic change in elevation was a result of the shifting tectonic plates during the earthquake, which caused a portion of the seafloor to rise, lifting the land above it. Now let's look at rapid coastal recession. Here are factors that can cause rapid coastal recession. Destructive ocean waves with a long fetch play a significant role, as waves that travel over a long distance gather more energy, leading to stronger wave action upon reaching the coast. This can cause more intense erosion of the coastline. Additionally, rocks with many bedding planes and joints are more vulnerable to erosion, as these natural weaknesses in the rock structure provide pathways for water to penetrate and break the rock apart, increasing the rate of erosion. Coastlines with soft geologies, such as unconsolidated sediment or softer rocks like sandstone, are also more prone to rapid recession because the materials are less resistant to wave action and weathering processes. Cliffs with structural weaknesses, such as those with a specific type of dip or orientation, are more susceptible to collapse or slumping, which can accelerate coastal retreat. Finally, cliffs vulnerable to mass movements, particularly those made of clay, are at high risk of rapid recession. Clay-rich cliffs tend to absorb water quickly, becoming saturated and prone to slumping or sliding, further contributing to the loss of land along the coast. All these factors combined can lead to significant and rapid coastal erosion. Humans can cause rapid coastal recession. An example of this is the Akosombo Dam. This reduced sediment flow down the river Volta, meaning coastal erosion increased in Ghana and neighboring countries. Interfering with a sediment source changes the equilibrium and can impact coastal recession because less sediment is available. The rest of this section is covered in my case study video on the Holderness Coast, a location that experiences rapid coastal recession, allowing me to cover these concepts in more detail. There we will look at how rates are not constant and vary. The link is in the description. Let's continue and look at coastal flooding. Here are areas at an increased risk of coastal flooding. They are coastal plains, low-lying land, estuaries, and river deltas. A good case study to explain why areas may be at increased flood risk is Bangladesh. Over the next slides I will cover 6 factors that made it a country at increased risk. Low-lying geography increases flood risk. Bangladesh is situated on the Bengal Delta, which is one of the lowest and most flood-prone areas in the world. Much of the country is below sea level or very close to it, with large parts of its land being less than 10 meters above sea level. Secondly, high population density. The country has a very high population of over 160 million people concentrated along its coastal regions. This makes large numbers of people and property vulnerable to coastal flooding. Monsoon climate and cyclones. Bangladesh experiences seasonal monsoons, which bring heavy rainfall and flooding. In addition, it is frequently affected by tropical cyclones, especially during the storm season of May to November. These storms can lead to extreme storm surges, causing rapid flooding in coastal areas. Another factor is sea level rise. Due to global warming, As we saw earlier, sea levels are rising, and Bangladesh is particularly vulnerable due to its low-lying coastal position. Even a small increase in sea level can lead to significant flooding, affecting agriculture, infrastructure, and human settlements. Here are the final two factors. Bangladesh is crisscrossed by numerous rivers, which often overflow during the monsoon season. These rivers can also bring in sediment, which naturally raises the land level, but human interventions have disrupted this process, making the land more vulnerable to flooding. Finally, deforestation and the loss of natural barriers increases risk in Bangladesh. The loss of mangroves and coastal forests, which act as natural barriers against storm surges and coastal flooding, has increased the flood risk. Without these barriers, the country is more exposed to the impact of storms and rising sea levels. Now we will look at coastal flooding and climate change. Rising sea levels increase flood risk. As global temperatures rise, polar ice melts and thermal expansion causes sea levels to rise, increasing the likelihood of coastal flooding in low-lying areas. Climate change also creates an increased rainfall and storm intensity. Warmer temperatures lead to glacier and snowpack melt, especially in mountainous regions, which increases river discharge and the risk of river flooding downstream. And there are also more frequent and intense cyclones. This is because warmer oceans provide more energy for tropical storms and hurricanes, increasing the frequency and intensity of storm surges. For information on how storm surges and extreme weather events can cause coastal flooding, watch my case study video on the 2013 North Sea storm surge. Link in description. Hello and welcome back to A-Level Geography Explained. In this video, we will be exploring the fourth and final inquiry question of the coasts topic. The three main subsections of the inquiry question covered are how communities are impacted by increasing coastal retreat and flood risk, different approaches to managing risk, and management plans. Let's begin. Flooding and coastal recession has many social impacts on communities. These include the loss of homes, the displacement of families, the loss of livelihoods, negative health impacts, and the loss of social amenities. Economic impacts include the loss of farmland, the destruction of businesses, huge insurance payouts, a loss of property value, and also the council lose money on repairs. For example, laying new roads. Let's look at impacts in developed and developing countries. In Australia, a developed country, predictions state that by 2100, sea levels will most likely rise by 55 centimeters. A rise of 1 meter could result in 116,000 homes being flooded, leading to property damage totaling around $72 billion. Commercial properties worth $87 billion would be at risk. $67 billion in road and rail infrastructure could be affected and potentially 5 power stations could be lost. 258 emergency service stations would be in danger and 75 hospitals at risk. Finally, 44 water and sewage treatment plants could be threatened. There would also be severe social consequences. These include the potential displacement of communities, livelihoods being lost, and a decline in the quality of life due to the loss of amenities. Additionally, coral reefs, including the Great Barrier Reef, could perish if they are unable to grow quickly enough to keep pace with rising sea levels, leading to a decrease in tourism revenue. Let's look at impacts on the developing country of the Philippines. Predictions are that sea levels could rise here by 60 to 100 centimeters. A 1 meter increase in sea levels could result in approximately $6.5 billion in property damage. In San Fernando, located in the northern part of Luzon, an estimated 123,000 meters squared of beach area could be lost, potentially reducing tourism revenue by $95,000 per year. Also, the fishing industry could see losses of around $168,000 annually. Socially, a 1 meter rise would impact roughly 2.3 million people, including 62% of the population in Manila, on the southern part of Luzon Island. Major sources of livelihood, including fishing and tourism, would be severely disrupted. The loss of amenity value, particularly the beaches in San Fernando, would also affect local quality of life. The social costs could be significant, especially since alternative employment opportunities in the formal sector are scarce, making it difficult for affected communities to find new work. Environmental refugees can be created as a result of coastal flooding and recession. This can be seen in the Maldives. Rising sea levels increase threat. The Maldives is at risk of being submerged due to rising sea levels, with much of the country less than 1 meter above sea level, leading to the displacement of its population. Loss of livelihoods. Climate change threatens key industries like tourism and fishing, as coastal erosion and coral bleaching reduce income opportunities for locals. Finally, migration to other countries. As the Maldives becomes less habitable, many residents may be forced to migrate to neighboring countries, creating environmental refugees and raising concerns for regional migration policies. Now we will explore methods of soft and hard engineering. Soft engineering attempts to work with natural processes to reduce coastal erosion and flood threat. Firstly, beach nourishment. This is where sediment lost by erosion or longshore drift is replaced. This means that the beach can protect the coastline by reducing wave energy and erosion. Costs are replacing sediment every few years. Next, cliff regrading and drainage. Cliff regrading involves reshaping the slope of a cliff to make it more stable and reduce the risk of landslides or collapse. By lowering the angle of the cliff, gravitational stress is reduced. Drainage removes excess water from within the cliff, which decreases pore water pressure and helps prevent mass movement. Together, these methods are effective in managing coastal erosion and protecting infrastructure near vulnerable coastlines. Dune stabilization is used to protect coastlines by preserving or restoring sand dunes. Techniques include planting marram grass to trap sand, installing sand fences, and restricting human access with boardwalks. These measures help dunes grow and act as natural barriers against coastal erosion and storm surges, while maintaining the beach's natural appearance. Hard engineering uses structures that aim to stop physical processes altogether or alter them to protect the coast. Riprap is where large igneous or metamorphic rock boulders, weighing several tons, are placed on the coastline to reduce wave energy. The dissipation in energy can lead to further deposition. Rock breakwaters are made of large boulders placed offshore, parallel to the coast. They absorb and deflect wave energy before it reaches the shore, reducing erosion and creating calmer waters behind them. This encourages sediment deposition and can help build up beaches. However, they can be expensive and may impact coastal ecosystems and sediment transport. Seawalls are solid barriers built along the coastline to protect land and property from wave attack and coastal erosion. They reflect wave energy back into the sea, preventing erosion of the base of cliffs or the land behind. Revetments are sloping structures placed at the base of cliffs or along the shoreline to absorb and dissipate wave energy. Made from materials like wood, concrete, or rock, they reduce the force of incoming waves and protect the coast from erosion. Finally, groins are wooden, stone, or rock barriers built at right angles to the coast. They trap sediment moved by longshore drift, helping to build up the beach and provide natural protection against erosion. Here are the advantages and disadvantages of soft engineering. Advantages include being environmentally friendly, cheaper than hard engineering methods, and renewable. They blend into the natural landscape, meaning they are less of an eyesore. They promote diverse plant and animal life and are typical lower maintenance than some hard engineering methods. Disadvantages include less immediate protection and being vulnerable to extreme weather. They may be temporary solutions or have unpredictable results. They are harder to implement in urban zones. Here are the advantages and disadvantages of hard engineering. Advantages include being an effective protection method. They provide long-term stability and control over natural processes. They can protect high-value land and have predictable outcomes. They can have an immediate impact protecting coastlines. Disadvantages include being incredibly expensive, having a high environmental impact, and not being aesthetically pleasing. They can worsen erosion nearby through sediment starvation. Frequent upkeep and repair are needed. Let's look at how sustainable coastal management is used in the Maldives. Coral reef protection. We can protect coral reefs by establishing marine protected areas and restoring damaged sections. This not only reduces coastal erosion but also supports rich marine biodiversity. Coastal vegetation. Replanting mangroves and native vegetation help stabilize shorelines. Their roots hold the soil together and reduce the impact of waves, slowing down erosion. Beach nourishment. Adding sand to eroded beaches helps restore natural coastlines. It also acts as a buffer, protecting infrastructure from storm damage and rising sea levels. Sustainable tourism. Promoting eco-friendly resorts and proper waste management helps reduce the environmental impact of tourism. This supports long-term conservation of coastal ecosystems. Climate change adaptation. To build resilience against rising sea levels and extreme weather, we can invest in solutions like floating islands, elevated infrastructure, and advanced flood protection systems. Integrated coastal management. By working together across sectors, such as government, local communities, and environmental groups, we can balance development needs with long-term coastal conservation. Renewable energy. Switching to clean energy sources like solar power helps reduce our reliance on fossil fuels, playing a key role in tackling climate change and protecting our planet's future. The final part of this video is on shoreline management plans. SMPs were introduced by the government in 1995. SMPs are an approach to coastal management that involves all stakeholders in making decisions about how coastal erosion and coastal flood risk should be managed. They aim to balance economic, social, and environmental needs and pressures at the coast, and there are 22 in England and Wales. They are managed by coastal groups, made up of local councils and the Environment Agency. There are four main types. Firstly, no active intervention. This strategy lets nature take its course. Erosion and coastal flooding occur and cliff lines gradually retreat. It is often used when coastal land is of low value, for instance farmland, or when only a few properties are threatened with erosion. It can also be used when rates of erosion are rapid and the engineering challenge of defending the coast is too great. Managed realignment is a halfway house between holding the line and doing nothing. Coastlines are allowed to erode and flood, but gradually. Some defenses might be constructed in the future to prevent continuous loss of land or extensive flooding. An example of this policy is at Spurn Head Spit at the southern tip of the Holdres coast. The plan is to allow the spit to erode but move inland over time, intervening to prevent it being breached by the sea. Hold the line is used when coasts are deemed high value. The value could be due to urban development and industry. In some cases, rare ecosystems might be protected in this way. Engineering is used, usually hard defenses. This strategy could be temporary in some places, as rising sea levels may make it impossibly expensive to maintain in 50 or 100 years' time. The final type is advance the line. This strategy is fairly rare in the UK. It involves building defenses out to sea. Effectively creating new land. It is very expensive and it is also likely to be affected by future sea level rise, so defenses built today would need to be raised and improved in the future. When making a plan, cost-benefit analysis is carried out. In coastal management, the first step is cost identification. This involves considering capital costs, maintenance expenses, and also environmental and social costs, such as impacts on ecosystems or the potential displacement of communities due to new infrastructure. Following this, benefit identification takes place. This considers a range of positive outcomes, including economic benefits like property and infrastructure protection, social benefits such as the preservation of local communities, and environmental benefits, for example, the protection of important coastal habitats. Risk assessment is then carried out to evaluate the potential consequences of taking no action. These risks might include damage to homes and infrastructure, loss of livelihoods, or increased vulnerability to storm events and sea level rise. A sensitivity analysis is used to test how different variables, such as changes in sea level, storm frequency, or population growth, could affect the outcome of a strategy. This helps account for uncertainties and ensures greater adaptability. Finally, the decision-making stage involves selecting the most cost-effective strategy that delivers the greatest net benefit. This often requires balancing hard engineering approaches with more sustainable, soft engineering methods, depending on the specific needs and risks of the area. Disagreements can occur over shoreline management plans between key players. There is often tension between prioritizing economic growth and implementing protective measures that can limit development, especially in coastal areas. Local communities may oppose relocation due to the potential loss of their homes and livelihoods, particularly in regions where the environment is central to their way of life. Wealthier areas tend to benefit more from coastal management plans, while poorer communities often bear the environmental and social costs without receiving the same level of protection. Disagreements can arise when local residents aren't adequately consulted about the impacts of shoreline management plans on their land and livelihoods, leading to a sense of exclusion. Finally, there is an ongoing debate over the balance between hard engineering solutions, like sea walls, and nature-based approaches, such as mangrove restoration, with questions around how to balance immediate effectiveness with long-term sustainability. I hope this video helped your revision. Please subscribe and check out more of my revision videos. Goodbye.